All right, so now we're starting into projectile motion. We have finished vectors and being able to divide vectors into its individual components, its two separate pieces, and the combination of those two pieces is what gives us the vector. And now we're going to apply that here with projectile motion. The YouTube video that you just watched demonstrated that it's a classic physics demo. It demonstrated that an object that is released and an object that is shot horizontally with an initial velocity will hit the ground at the same time. In other words, it takes the exact same amount of time for it to fall. So here is kind of a picture of that idea going on. And as time goes along, right, everything parallels perfectly. Everything parallels perfectly, right? In other words, just because something is launched with an x-axis velocity, right? Just because something is launched with a vx, or a velocity in the x-axis, it doesn't actually change what's happening in the y-axis. The y-axis component is independent of the x-axis component. So let's look at that a little bit more in depth. So let's move that picture out of the way, and let's put another one up here. That shows a cannon. So we're launching a cannonball, I guess, horizontally here. And so the actual arc of the cannonball is like this right here, projectile motion. And obviously as you go in time, it's going to curve downwards. But you can divide your projectile motion into two components, right? This is the actual arc, but there is an x component and a y component. The y component behaves just as if the cannonball was dropped, okay? So it's accelerating because of gravity, pulling it down, right? So it's with each passing second, notice the distance grows exponentially, right? So gravity is accelerating the cannonball downwards. At the exact same time, though, the x-axis is experiencing constant velocity because there is no acceleration in the x-axis, okay? Everything is exactly the same. The combination of these two components, your x component and your y component, is what gives you the actual projectile motion graph. All right, so let's actually work a problem like that. Here I've got a 200-meter cliff, right, and I'm going to launch an object off horizontally at 32 meters per second. Now the actual path this object's going to take is going to look something like this, right, curving down. Notice that it, towards the end, curves a lot more rapidly. That's the acceleration of gravity pulling it downwards, right? So gravity is pulling it downwards, and so the velocity is becoming greater and greater and greater in the y-axis as time ticks along, while we're getting constant velocity in the x-axis. So the question that I want to answer with this one, if I throw a ball off a 200-meter cliff at 32 meters per second, how far away is it going to land? In other words, what is its delta x going to end up being? So the way we solve projectile motion problems, it comes from the idea of vectors. We can take an actual arc, an actual movement, right, like here in a projectile motion, and divide it into its individual pieces. Here, an x piece and a y piece, right, an x piece and my y piece here. So the idea is these two separate pieces, I work them as if they're two separate problems. In the x-axis, I have constant velocity. In the y-axis, I'm going to have free fall. I drop an object and it falls to Earth. And the combination of those two motions is what actually gives me my projectile motion type arc. But I don't have to worry about trying to calculate the projectile motion arc. I can calculate the two separate pieces, the x component and the y component of this motion, and the addition of these two at the end is what gives me the actual answers that I need. So here, let's write down everything we know. So step 1, draw a picture, done. Step 2, write down everything you know and what you're looking for. So in the x-axis, I know the velocity here. The velocity is going to be, I'm going to label it Vx. The velocity is going to be 32 meters per second. I know I'm looking for delta x. That's the end goal. I don't know how long it's going to take here, and I'm actually not going to put a question mark there because the time isn't the end goal. In the x-axis, it's constant velocity, right? The object continues to move forward at a normal and constant speed. Think about the picture that I showed you previously. There is no acceleration propelling the object forward, right, in the x-axis. There's nothing slowing it down the x-axis. That's the horizontal going straight across. Instead, it's just going to keep on going at 32 meters per second. We haven't talked about Newton's laws yet, but an object in motion will remain in motion. So if I give it 32 meters per second going in the x-axis, that 32 meters per second, it's going to keep going in the x-axis. The y-axis velocity, likewise, the initial velocity, starts out as 0. There is no velocity going straight up and down whenever you first launch it, right? But gravity, the acceleration of gravity, negative 9.81, starts causing it to speed up, right? I do know delta y. Delta y is going to be negative 200 meters, and I gave myself a decimal there for sig figs. And by the way, you'll see me writing time in. Time is going to be the critical factor in all these projectile motion problems. It's the bridging gap between the x and the y axis, between the constant velocity piece in the x axis and the free fall acceleration of gravity piece in the y axis. And that's why I had you go ahead and watch that YouTube video really fast. Because I want you to understand time is the same. The time it takes for the object to go out in the x-axis is the exact same amount of time that it takes for the object to fall. That's the addition of those two is what gives you projectile motion. So I'm looking for delta x. So let's go ahead and let's think here. This is constant velocity. I only have one equation I can use in the x-axis. Vx equals delta x over t. But a slight problem here with this. I only know Vx. I don't know t, right? I don't know enough information. I know 32 equals delta x divided by t. That's not enough information to solve for delta x. But if I could figure out what the time was, how long this object was in the air, then I could tell you, hey, I could solve for delta x very easily. Where could I get that time from? The answer is the y-axis. So I come over here to the y-axis, I look at everything that I know, right? And I know I don't know time yet, and I'll go ahead and write in final velocity also here. But we don't care about final velocity in this case. Instead, I'm going to solve for time. So I'm going to pick an equation that works for me well to be able to solve for time in the y-axis. And that's going to be delta y equals VIT plus 1/2 AT squared. So negative 200 equals 0 times t plus 1/2 negative 9.81 t squared. Just to go ahead and give you a heads up on this, you're going to see this sort of situation in projectile motion problems over and over and over again. The x-axis is always constant velocity because there is, unless your object that you're launching off has rocket engines to accelerate it forward, right? It's going to go at a constant velocity in the x-axis. In the y-axis, right, you actually have gravity pulling it down, and this equation is a great one because most of the time you know the initial velocity of the object and you need time in there, especially if you're going to take that and bridge that over into the x-axis, right? So the goal here is to solve for time. Negative 200 equals 0 times t is 0, so I don't even have to worry about that. 1/2 negative 9.8 is negative 4.905. 0.905 t squared. So now I'm going to divide both sides by negative 4.905. Divide by negative 4.905. And then I'm going to square root both sides. So 40.77 approximately equals t squared square root. and t comes out to be 6.39 approximately, 6.39 seconds, because once again the units here, meters per second squared, right? The velocity was in meters per second, so all my time units should be in seconds. Great. Now I have a time that I now can take and plug in over here. So I have 32 equals delta x over 6.39 seconds. So multiply both sides by 6.39, and I get delta x is 204.33 meters, 34 meters, with I have only 2 sig figs right here. So I'm going to have to call this, because the sig figs rounding from, I'll actually put down my 204, but that's not right, right? This is going to have to become 200 meters, and with a line above that 0 right there. All right, so once again, the main idea on how you're going to solve projectile motion problems is this concept that we can divide things into components. An x component, gravity-free, it's just whatever happens in the x component, and that is going to be constant velocity, right? However much you launch it with, that's how much it has the entire time for the velocity, right? Constant velocity there. In the y-axis, though, you actually have acceleration of gravity, right? Acceleration of gravity, pulling it downwards. An initial velocity of 0 if it's launched horizontally, right? And then speeding up as it comes down. The combination of a constant velocity in the x-axis and accelerating in the y-axis is what gives us our projectile motion arc. Okay, so now whenever you add these two components, you're going to actually get the arc that you need. Time is the critical factor in this, because it takes the exact same amount of time for the object to come all the way out, constant velocity in the x-axis, as it does free fall in the y, giving us the arc. So the bridging factor that you're going to find in all these problems is going to be time.